right, so here's the screencast for solutions. So we're going to talk a little bit about what a solution is and some of the basic properties. So here's your essential question. What are the basic properties of a solution? We're going to be calculating molarity as well as figuring out dilution. So properties of solutions. A solution is a homogeneous mixture between two or more substances. So you take two things, mix it together, and if they're evenly mixed, then it's a solution. They can be solids, liquids, or gases. So a solute is the component that is present in the lesser quantity. So if you have two liquids that are mixed together, the one that has the lesser amount or the fewer molecules, that's the solute. And then the solvent is what's going to be present in the largest quantity. We usually think of like dissolving something in water. What you dissolve is the solute, the water is the solvent. And so we would then call it an aqueous solution if it's a solution where there is a solvent that is water, so something dissolved within water. But it doesn't have to be. So examples of solution: air, oxygen, and several trace gases are dissolved in the gaseous solvent of nitrogen. So nitrogen's a solvent because it's the highest quantity. All the other ones are dissolved within it. Any of our alloys like brass or other homogeneous metal mixtures like steel, in the solid state, we call those things alloys. And then obviously liquids, that's the one that everybody thinks of. So general properties of liquid solutions: they're usually clear or transparent with no visible particles. So something is dissolved within it and you can't see it anymore. It may be colored or colorless. We think of them as electrolytes. The electrolytes are formed from the solutes because they're ionic compounds that have dissolved, and so they have a charge. And they would have a positive or a negative, or positive and a negative charge. The ions break apart in that solution, so it would conduct electricity. That's all it means to be an electrolyte. Non-electrolytes do not dissociate or do not dissolve, so you're not going to form a solution with them. They would just settle to the bottom, and you're not going to have the positive and negative charges. The volume of the solute and the solvent are not additive. So like if I had 50 mils of water and then I added 10 grams of sodium chloride to it, the volume doesn't change. It just dissolves within the space. The sodium chloride dissolves in the space within those water molecules. So it doesn't become like 60 mils of solution, so they are not additive. 1 liter of ethanol and 1 liter of water does not give 2 liters of solution. So solutions and colloids, you should have learned about this in physical science, but colloidal dispersion contains solute particles which are not uniformly distributed. So the particles are a little bit bigger, and you can actually maybe see them. Think like muddy water. You can see the particles in there. If the particles are smaller than 1 nanometer, we call it a solution. You're not going to see anything. But we would call it a colloidal dispersion if the particles are between 1 and 200 nanometers. And then if they're larger than 200 nanometers, it's eventually going to form a precipitate and it'll settle to the bottom. So you'll have this material settling out, depending upon your particle size. So the Tyndall effect is the ability of a colloid to scatter light. You're going to see a haze when you're shining light through a colloid. So if it's a solution, it's going to pass right through without scattering. But here you can see this like band where the light is, and you can see the actual particles in there. So this would be considered a colloid. We've already talked about solubility a little bit, but the degree of how much a particular solute will dissolve is based on a lot of different things. In the lab, we changed the temperature to see if that would affect solubility. We stirred it to see if that would affect solubility. But polarity, the more different the solute and the solvent are, the lower the solubility. Think like oil and water. They are completely opposites on the polar and nonpolar scale, so they don't dissolve in each other, or the oil doesn't dissolve in the water. Temperature usually increases solubility, not always, but for the most part it does. And then pressure usually has no effect. If solubility is of a gas in a liquid, then it's directly proportional to the applied pressure. The more pressure you have, the more gas is going to go into that liquid. The less pressure you have, the less gas. But pressure usually doesn't have an effect. So in the solutions, we call them saturated, supersaturated, or unsaturated. A saturated solution just means that it's holding all of it that it can at that particular temperature. It can't hold any more. There's no more room. A supersaturated solution means it's holding more than it should be able to. So how do you make a supersaturated solution? you're going to heat up the solvent, like the water. You're going to heat it up, and you're going to saturate it with the solute at that higher temperature, and then you allow it to cool back to room temperature. Sometimes the excess will precipitate out, but if it doesn't, we call it supersaturated. This is how you can make like a syrup solution with sugar and water. You boil the water and you dissolve as much sugar as you can in the boiled water, and then you let it cool back down. Well, that solution will then have more sugar in it than it should have at room temperature. And sometimes you can get it to stay, sometimes you can get the sugar to crystallize out of it. So solubility and equilibrium. If excess solute is added to a solvent, some of it will dissolve. So at first, the rate of dissolution is large, and then later you get the reverse reaction, the precipitate. It's going to occur more rapidly. So it's just like any equilibrium. You get a whole bunch dissolving at first, and then it slows down to where then some of it undissolves. And then you find this equilibrium between the dissolved and the precipitate. So it being dissolved and it being a solid. So at equilibrium, there is some that's dissolved and some that's undissolved in the solution. So we would call that a saturated solution is an example of a dynamic equilibrium because it's constantly changing between stuff that is dissolved and stuff that isn't. So Henry's law deals with gases. Henry's law, the number of moles of a gas dissolved in a liquid at a given temperature is proportional to the partial pressure of the gas above the liquid. So gas solubility is directly proportional to the pressure of the gas in the atmosphere. That's where right above that liquid, if you put more pressure, then more dissolves. If you have less pressure, then less dissolves. Those gas particles are going to be dependent upon the pressure of the air above them on how much is going to dissolve. Gases are most soluble at low temperatures. That's why cold water holds more oxygen than warm water. And solubility decreases significantly at higher temperatures. So like carbonated beverages, CO2 is less dissolved when it's warm. That's why it's more carbonated when it's cold. Respiration facilitates oxygen and carbon dioxide exchange in the lungs. And this just happens better when it's at a cooler temperature. So our next essential question for this is what is molarity and how is it calculated? We've talked about molarity a little bit. You've seen it when we've said the concentration of things. So the concentration is just the amount of solute that's dissolved in a given amount of solution. The concentration has an effect on the physical properties, its melting and boiling point, its chemical properties, how reactive it is. Weak solutions, ones that don't have very much dissolved in them, aren't as reactive as concentrated solutions. And you saw that in your equilibrium lab, where you had 1 molar hydrochloric acid, 2 molar, and 3 molar. The 3 molar was way more concentrated because there was more hydrochloric acid in it. So mass volume percent is basically exactly what it is. So concentration is the amount of solute divided by the amount of solution. A mass volume percentage is where you take the grams of solute divided by the milliliters of solution times 100, and that's going to tell you what percentage of your solute is. It's a 3%, it's a 10% solution, it's a 50% solution. That's based on how much solute you add and how many milliliters. Whereas the concentration is just any amount, not just grams or milliliters, it's any amount of solute divided by the solution. So the amount of solute equals the mass of solute in grams. The amount of solution is the volume in milliliters. And if you divide those and times it by 100, you get the mass volume percent. So here's an example of calculating the mass volume percent. We will work through these examples in class. Here is another one, an example of a mass volume percent that we will work through together in class. You can also do mass percent. The grams of solute divided by grams of solution. So this one right here would be like if you had 2 solids and you were making a solution out of it. So calculate the percentage of platinum in a gold ring. So we're going to go ahead and work through this one in class. You've probably heard concentrations of things in like ppm or ppt, parts per thousand or parts per million. A lot of times they'll tell you like how much lead is in something or how much lead is in your water, and they'll tell you in parts per million. As percentage is the number of parts per 100, parts per thousand and parts per million change the calculation just by orders of magnitude. So it'll tell you how much is in there based on those values instead of based on 100. So you would do grams of solute divided by grams of solution times 10 to the third to get parts per thousand. Then you would do that same calculation times 10 to the sixth to get parts per million. They are most often used in very dilute solutions like our water when we're trying to determine how much stuff is dissolved in our water. Concentrations based on moles, this is where we get into molarity. Chemical equations represent the relative number of moles. Remember, the coefficients tell you how many moles of reactants you have producing a set number or a set mole amount of products. So many chemical reactions occur in solutions where it's most useful to represent concentrations on a molar basis. So that's where we get into what is molarity. Molarity is moles per liter. So moles of your solute per liter of solution. And it's symbolized by a capital M. It's defined as the number of moles of solute per liter of solution. So all you have to do is use this calculation. If you know two of the three variables, you can calculate the third one. So here's a calculation we will work through in class. All you do is substitute what you know and solve for what you don't. Here's a couple more examples on how to do a little conversions with it to go from grams to moles and then milliliters to liters to find your moles per liter. So we will work through this example in class. Dilutions are kind of cool in that you just follow a simple equation and you can determine what concentrations things are after you dilute them. It's sometimes useful to dilute solutions down. Like a pharmacist would do a lot of dilutions based on different weights and ages of kids on the different amounts of medicines they can take. So you might have to dilute something. But dilution is required to prepare a less concentrated solution from a more concentrated one. So you're going to have your molarity of your solution before you start, what the molarity needs to be after you start, what volume you're starting with, and then the volume after. And you're going to know 3 of those variables, so you just solve for the 4th one. So you use this equation, and we will go through and work this example problem of a dilution problem, just plugging into that equation. We will work through this in class. Some concentration dependent properties, so properties that are dependent upon the molarity. These are called colligative properties. They depend on the concentration. So colligative and concentration. Think of those two together. These properties change as you have more or less solute particles. So vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So vapor pressure lowering would determine how much energy it takes for it to go from a gas to a liquid. Boiling point elevation, going from a liquid to a gas. Freezing point depression, meaning it would take more, it would have to be colder to get it to go to a solid. We rely on these colligative properties for a lot of things. I think of like when they add salt to roads, or they add, you put salt on your driveway or your steps. As the concentration increases of the salt, it lowers the it lowers the freezing point of water. So you get freezing point depression. So a little bit on vapor pressure of a solution. It results from the escape of solvent molecules from liquid to gas. So as something is going from a liquid to a gas, presence of the solute hinders that escape. So it lowers the equilibrium vapor pressure. Freezing point depression, just like we talked about, where you form or you put something in there and it slows the rate at which the liquid becomes a solid. You get boiling point elevation. If a solute is present, it increases the boiling temperature. So you don't want to add salt to water until it starts to boil, and then you can salt your water if you're making pasta or something like that. Okay, molality is the last thing to talk about. It is solution concentration is expressed in mole-based units, but instead of it being moles per liter, we do moles per kilogram of solvent. So it's just a little bit of a different unit. We think of molarity as moles per liter, molality as moles per kilogram of solvent. This works really great if you're working with solids. So that concludes our discussion on solutions. We will work through a bunch of practice problems in class on dilutions and molarity problems.